Good morning, student. Last class we discussed about the bandwidth derivation and also quality factor of series resonant circuit, and also coming to the parallel resonant circuit. So tank circuit resonant frequency derivation, and also practical inductor, practical capacitor derivation, and one problem I have to see in the last video. Now we go for the quality factor for parallel circuit. Already know that what is quality means. Quality of a inductor or capacitor in a given circuit. That means performance of the inductor or capacitor for a given particular circuit. That means quality factor. Quality factor is mainly defined as the 2 pi into maximum energy stored in the inductor or capacitor divided by the energy dissipated per a nearby the resistor. Simply say the quality factor must is also defined as voltage across the inductor or capacitor to the total voltage. That means so VL by VL or VC by this is also quality factor. Voltage across the capacitor or inductor divided the total voltage of the source given circuit. That may quality factor may depend also like this also. Now go derive the quality factor for parallel resonance for inductor. Whereas in series resonance and for series resonance for inductor, for capacitor in terms of RLC you have to derive it. Now we have to go for the parallel resonance. The values of quality factor for series resonance is exactly inverse of the quality factor for parallel resonance. That is, so whereas in series resonance the quality factor for inductor is omega L by R, but here R by omega L. So 1 by omega CR for capacitor in series resonance, here omega CR, and 1 by R root L by C. So in terms of RLC, now here so R root C by L, like that. Exactly inverse of the quality factor of parallel resonance is exactly inverse of the quality factor of series resonance. How will you see that? For inductor, maximum energy stored, as we know that, half Li square, and maximum energy dissipated in nearby resistor is, there is nothing but you have considered this is a practical inductor. Practical inductor is nothing but, so a inductor in series with a resistor. An inductor in series with a resistor, the energy stored in the inductor is half Li square. So that energy must be dissipated nearby the resistor is nothing but IRMS square RT, that is I maximum by root 2 square into RT, I maximum square RT. Now, but so what is this inductor current? Half L IL square. Inductor current is nothing but V voltage across the inductor is IL into XL. Now IL is equal to V by XL, but we know that XL is equal to omega L. So that may be substituted in the given equation, and current to the resistor I is equal to V by R. So in the denominator, so in place of IL, I substitute V by omega L. In denominator, in place of I, we substitute I is equal to V by R. Then we are getting 2 pi here, V square cancel, 1 R cancel, L cancel. So 2 pi F R omega L square L. So here 1 by T is nothing but F. That's why I write here. Now 2 pi F is nothing but omega R by omega square L. Omega cancel, R by omega L. Quality factor is for parallel resonance for inductor is R by omega L. It is exactly inverse of the series resonance quality factor for inductor. So for that is omega L by R, but here R by omega L. Now go for the capacitor. Maximum energy stored in the capacitor is half CV square, energy dissipated per cycle resistor, on half I square RT. But here resistor, this is also practical capacitor. There is nothing but a capacitor in series with resistor. Here I is equal to V by R. That means substitute 2 pi into half CV square. Half I means V by R square RT. When cancelled each term, and remaining is 2 pi CRF. 1 by T is nothing but F. 2 pi F CR. 2 pi F CR. So that is 2 pi F is nothing but omega CR is the quality factor for capacitor in parallel resonance. Whereas in series 1 by omega CR, here omega CR. Now in terms of RLC, so we know that quality factor is equal to resonant frequency by bandwidth. Resonant frequency bandwidth is nothing but the difference between the two cutoff frequencies, higher cutoff frequency minus lower cutoff frequency. But we know that resonant frequency 1 by 2 pi root LC and difference between these two 1 by 2 pi RC cancel 2 pi and some adjustment will be then Q is equal to R into root C by L. This is the quality factor in terms of RLC parameters in parallel resonant circuit, whereas in series resonant circuit 1 by R root L by C, but here R root C by exactly inverse of the series resonance. Quality factor of a parallel resonance for each and every term, so must be the inverse of the series resonance. Now we have to derive the relation between the quality factor and bandwidth. Quality factor and bandwidth, that is, we know that quality factor is equal to omega naught RC. Omega naught means 2 pi F naught RC, and so if you can put F naught, this 2 pi RC, that is 1 by 2 pi, I can write like this 1 by 2 pi RC. So what is this one? 1 by 2 pi RC is nothing but bandwidth. 1 by 2 pi RC is nothing but F2 minus F1. So F naught by F2 minus F1. So this is F naught by bandwidth. So this is the relation between quality factor and bandwidth. Now another topic is, now go for the problem. They given a parallel fixed practical inductor and practical capacitor. They given the values of RL is equal to 5 ohms, RC equal to 10 ohms, and inductive capacitive reactance is minus j12 ohm. Now we have to find out the inductor value. They given practical inductor, practical capacitor connect to AC, connect to a supply system. So now we have to find out the inductor value. As you derived the formula for practical resonant frequency formula for practical inductor, practical capacitor. First of all, we have to calculate the individual admittance for each branch. So then we have to calculate the L value. First of all, as usual, so for this branch, so we can consider Y1, for this branch Y2. So now Y1 is equal to 1 by Z1, that is nothing but 1 by 5 plus JXL. So result is, so 5 minus JXL minus 5 minus JXL. So 5 minus JXL by 5 square plus XL square. Or similarly, branch 2, 1 by Z2, Y2 equal to 1 by Z2, that is 1 by 10 minus J12. So rationalize that one, 1 by 10 minus J12, you multiplied by 10 plus J12 into by 10 plus J12, that is 10 plus J12 by 10 square plus 12 square. Now total admittance, Y is equal to branch 1 admittance plus branch 2 admittance. So that is 5 minus JXL by 5 square plus XL square, 10 plus J12 by 10 square plus 12 square. Now you have to separate the real parts and imaginary parts. So 5 plus 5 square plus XL square, 10 by 10 square plus 12 square, plus J times of 12 by 10 square plus 12 square minus XL by 5 square XL square. So this is the total admittance of the given parallel circuit. Now to find out the at resonant condition, the circuit behaves as a resistive. That means imaginary part of this equation must be equal to 0. That's why imaginary part of that equation, that is 12 by 10 square plus 12 square minus XL by 5 square plus XL square equal to 0. So to solve that one, so 5 square 10 square plus 12 square is nothing but 244. 244 XL into 12 into XL square plus 12 into 25, that is 300. So totally XL square plus minus 203 XL plus 25. Find out the roots of this one. We are getting 18.98 ohms or 1.32 ohms. But we have to find out the L value. XL is equal to omega L. Therefore L is equal to XL by omega. So L is equal to XL value 18.98 by omega. Omega is nothing but 2 pi F. 2 pi into 50, that is 314. To find out the L is equal to 18.98 millihenry, otherwise 1.32 millihenry. Go for the another problem, like that you have to calculate the L, or sometimes C also, right? So otherwise find out the frequency as usual. Suppose they given another parallel circuit, that is tank circuit. To find out the resonant frequency, dynamic resistance, and also quality and also bandwidth. So practical tank circuit in the sense practical inductor in parallel with a fixed capacitor. The given practical inductor value internal resistance value is 2 ohms and inductance is 1 millihenry, that is 1 into 10 power minus 3 henry, and fixed capacity is 10 microfarad, that is 10 into 10 power minus 6. Now what is the resonant frequency formula for tank circuit is nothing but 1 by 2 pi root 1 by LC minus RL square by L square. Already, so last class I have derived this formula also. So 1 by 2 into 3.14 square root of 1 by L 1 into 10 power minus 3 C 10 into 10 power minus 6 minus RL 2 square by L 1 into 10 power minus 6 square. For getting this one 1560.2 Hz. Now find out the dynamic resistance. Dynamic resistance is nothing but in the sense impedance of a parallel circuit, that is L by RC. So L value 1 into 10 power minus 3, 2 into 10 into 10 power minus 6, that is getting the RD. Dynamic resistance or impedance of parallel circuit is 50 ohms. And last, find out the bandwidth. Bandwidth is F0 by Q, but we don't know Q value. For that, we find out the Q value. Q factor for parallel resonant circuit is R into root C by L. We know that R value 2, we know that C value 10 into 10 power minus 6, L value 1 into 10 power minus 3. We are getting 0.2, very low Q factor. Very low Q factor means bandwidth is very high because these two are inversely proportional. So we are getting bandwidth is 7801 Hz. Last topic of the series resonance and parallel resonance topic circuit. So comparison between series and parallel resonance, most important. So what is the difference between the series and parallel resonance? Generally, what is meant by series resonance circuit? The resonance occurred when net reactance must be equal to 0. That means capital X must be equal to 0. That is, the difference between the inductor and capacitor reactance must be equal to 0. They cancel to each other. That is the series resonance. Whereas in parallel resonance, net susceptance equal to 0. The resonance occurred where the net susceptance B equal to 0. That is BL minus BC equal to 0. So coming to the another definition. So series resonance we can also called as voltage magnification circuit. Always it will give the in terms of voltage. Voltage will be different in the series circuit. Current must be same. That's why. So voltage across resistor, that is VR is equal to IR, that is equal to V supply voltage. Coming to the, so here VR is equal to V, where VL is equal to Q times of the V at an angle 90 degrees. VC equal to Q times of the minus 90 degrees. So that's why. So series resonance circuit is also called as voltage magnification circuit, whereas so parallel resonance circuit is called current magnification circuit because of it is a parallel circuit, current will be different, IR, IL, IC. So IL is equal to QI minus 90 degrees and IC equal to QI plus 90 degrees. Now go for the another difference. So at resonance condition, current is maximum in series resonance circuit, whereas in parallel resonance circuit, at resonant condition current is minimum because of here at resonant condition impedance is minimum in series circuit. That's why current is maximum. Here impedance is maximum. That's why current is minimum. So already we know that the difference. That is this is the current waveform and this is the Z waveform. So at resonance condition, so Z is minimum. This is the Z minimum value. Current is maximum value. Current is maximum value. So coming to the another difference. So current at cutoff frequencies. In series resonance circuit, current at cutoff frequency is nothing but impedance at cutoff frequency is root times of the impedance at resonant frequency. That's why current is nothing but V by root 2 Z. So that is 0.2. 1 by root 2 is nothing but 0.707 times of the maximum current. Coming to this one, root 2 times. Just reverse. So this is 1 by root 2 times of the maximum current. This is root 2 times of the minimum current. So that is 1.414 times of the minimum current. Another one, in series resonance circuit, the circuit behaves below at resonant condition. At resonant condition, circuit behaves as a. So this is the impedance. So this is the resistor parallel. This is the XL value. This is Z value. This is the minimum. This is F0. So XC, XL. So below resonant circuit behaves as a capacitive nature. Circuit behaves as a capacitive nature. Above resonant frequency, circuit behaves as an inductor nature. At resonant frequency, circuit behaves as a resistor circuit. Coming to the parallel resonance circuit, the exactly difference. So it may act as inductor, it may act as capacitor. This may be equal to resistance. That means below resonant frequency, circuit behaves as an inductor circuit, whereas above resonant frequency, circuit behaves as a capacitor circuit. At resonant frequency, it may be resistor circuit. And the last difference is series resonant circuit is also called as acceptor circuit, whereas in parallel resonant circuit is also called as resistor circuit. So this is how the resonance topic in 4th unit of network analysis subject. Right? To see this video, please subscribe DBS Talks.